Probability theory. What is it and why do we use it? In this series, my goal is to help us understand and, more importantly, appreciate the science and tools behind probability. We will do exercises along the way to solidify our understanding. Let's get started. Starting with the what. Probability theory is the branch of mathematics that studies uncertainty. Probability gives us tools to quantify, reason about, and make prediction when outcomes are not certain. Now the why, and that is uncertainty as mentioned. For us humans, life is full of uncertainty. Will I arrive on time? Will my favorite team win tonight's match? Will we hit our sales goals this quarter? The truth is, we just don't know everything we need to know to be certain. So what do we do when we are faced with uncertainty? We guess, right? Sometimes our guesses are educated, based on experience, patterns, or a little bit of gut feeling. That's why we naturally say things like maybe, perhaps, or it's likely. Now, probability theory is basically guessing, but with a sound method. Instead of relying on gut feeling, we rely on well-established mathematics. Probability gives us a way to measure uncertainty, make smarter decisions, and model the world around us. Without probability, we're just throwing darts in the dark. With probability, we can make informed decisions, even when randomness is all around us. Probability theory has profoundly shaped engineering, the natural sciences, and the social sciences. This fact alone is truly remarkable when you think of it. We mentioned that probability is a tool for understanding uncertainty using the language of mathematics. In particular, probability builds directly on one of the simplest but most important mathematical ideas, which are sets. Probability is really just assigning numbers to certain sets in a structured way. We'll start by defining the sample space. The sample space, written omega, is the set of all possible outcomes of a random experiment. A random experiment is a process or action that produces an uncertain result, meaning that the outcome of that experiment cannot be predicted with certainty. So you already see that we are starting to talk about uncertainty here. Now we denote each of these individual outcomes with a small omega. This illustration of a Venn diagram shows the sample space omega with all of its outcomes omega 1 to omega 5. Now let's look at examples of a random experiment. If we flip a coin, the possible outcomes are heads and tails. So these two outcomes make up the sample space. Flipping two coins will result in either heads heads, heads tails, tails heads, or tails tails. Therefore, these four make up the sample space. The next one should be obvious for you. Rolling a die will result in 6 possible outcomes. The examples we just looked at has what is called a discrete sample space. Besides discrete, there is also a continuous sample space. Discrete sample spaces are when the sample space contains separate countable outcomes. So for example, a simplified random experiment of the weather tomorrow, resulting in either sunny, cloudy, or rainy. On the other hand, we have continuous sample space. That is when the sample space contains an interval or uncountably many points. An example would be choosing a random real number between 0 and 1. Here the sample space is the entire interval of real numbers between 0 and 1. It's very important to keep in mind that the sample space is the universe in which all uncertainty lives. Once the sample space is fixed, everything else, events, probabilities, random variables are built on top of it. We will talk about these terms in the future. Now that we know what outcomes and sample spaces are, we can define the core object of probability: events. An event is any subset of the sample space, omega. And this is the crucial point. Because it is a subset of sample space omega, events are also sets. They are collections of outcomes that satisfy some condition. For example, the event A is the temperature tomorrow between 20 degrees and 25 degrees. and the event A is a subset of it, as denoted here, between 20 and 25. Let's do some exercise. We'll use the random experiment rolling a die. Here we have 4 events from A to D, and our task is to define all of these events. Feel free to pause and try it out yourself. Alright, let's do it. Remember that the sample space consists of all of these outcomes from 1 to 6. And when we are defining events, we are creating subsets. Starting with event A, rolling an even number. Then it should be 2, 4, and 6. Next, event B, rolling a number larger than 2. That should be 3 and above. There we go. Event C, rolling a 6. Well, it should be just this single outcome. And remember, a set can contain one element. Now to event D, rolling nothing. Well, this is impossible because when you roll a die, you always expect at least one outcome. This is also called the impossible event, and we can denote that with the empty set. Always remember that when we define events, we are creating a set where the elements are picked from the sample space. Because events are sets, we can use set theory to describe how events interact. The structure of probability mirrors the structure of sets. Therefore, we can perform set operations on events. Here are some of them. Feel free to pause and do it yourself. Here we have the sample space omega with the events A and B and all of these outcomes from omega 1 to omega 6. Let's start with an union operator, A union B. This combines the set A and B. So it should look like this. The intersection A intersect B. This captures the overlap. That means it contains this single outcome, omega 3. The complement, for example, not A, consists of any outcome in omega that is not A. That means it's omega 2, omega 4, and omega 6. The universal event omega, well, this is just the sample space, the event that all happens. It's basically a redundant definition of the sample space. And you have the impossible event, which is the event that contains no outcomes, which we talked about in the previous slide. Here's another exercise. The third one already. Don't worry, it's through practicing that you develop a solid understanding. I don't want this to be a one-way lesson where I do all the talking. This time our random experiment is flipping a coin twice, and the sample space consists of outcomes of the 2 different coin flips. As you see here, heads heads, heads tails, tails heads, and tails tails. As usual, define the following events. I encourage you to pause the video and work on it yourself, and afterwards we'll go through it together. Hope you took some time and enjoyed the exercise. Let's do it together. The event A, where at least one of the flips is a head. It consists of 3 possible outcomes, where both flips results in heads, the first flip as heads, and the second flip as heads. Now to event B, where both coin flips show the same result. That consists of the outcomes where both are heads and both are tails. A complement. This means the event where the outcome is not in A. So you see here, we have 3 in A. That means the only one left in the sample space is where both are tails. You can also rephrase this as the event with no heads. Next to A intersect B, right? You have these 2 events, and the intersection is both heads, because this outcome is contained both in A and B. And to the last one, A union B, well, that has all of the outcomes, because we are combining both events A and B, and this is the same as the sample space. Let's look at this event B, where both coin flips show the same result. At this point, after working through these exercises, you might start to wonder What is the probability of this happening? This event contains two outcomes, and in the sample space, there are 4 possible outcomes in total. So 2 out of 4 makes the probability 50%, because we can assume that it is a fair coin. Now notice what we are doing here. We are already assigning a number, which is that 50%, to a set, in this case an event, which means we are already working with probability. We will explore this idea more formally in the next videos. Let's summarize. In this video, we learned about probability theory as a tool to work with uncertainty. We learned about the sample space, where it is a set of all possible outcomes of a random experiment. And we learned about events. Events are the building blocks of probability. Events are a set of outcomes. They are a non-strict subset of the sample space. This gives us a good foundation before we move to the mathematical parts of probability. By understanding sample spaces and events as sets, we've built a precise framework for describing uncertainty. In the next video, we'll use this framework to introduce the axioms of probability and show how probability is formally defined. So, take a moment to reward yourself, stretch, grab a coffee, or head straight to the next video. I'll see you then.